So let me introduce the speaker. Espen Tallaksen is the CEO of EmLogic in Norway. Espen is also the author and architect of the open source UVVM, so Universal VHDL Verification Methodology. He has a strong interest in pragmatic efficiency and quality improvement, and has given lots of technical presentations at various international conferences with great feedback. He is also giving courses on FPGA design and verification worldwide. So today, his presentation will focus on the requirement coverage, specification coverage feature of UVVM.
Thank you. Can you hear me? Yeah, good. So before I start, just want to mention that I'm from a company called EmLogic. It's an independent design center for embedded systems based in Norway. Established only 4 years ago, and we're today 48 people, out of which 21 are working in FPGA. So we had a steep ramp up. We are doing a lot of work on the UVVM, and we also are course providers, so we do separate courses on FPGA design and FPGA verification worldwide, but lately mainly online. Okay, so what is UVVM? Well, it's the Universal VHDL Verification Methodology. It's for verification of FPGA, ASICs, and CPLDs. It's verification library and methodology. It's free, it's open source. Absolutely everything is free and open source. And it's used by quite a few designers worldwide. And if you look at the FPGA VHDL designers, that number is even higher. The good thing about UVVM is that it results in you making a far better test bench architecture, as Marcus just showed you. That means you're going to be more efficient and you're going to have better quality. So improves verification efficiency and assures this quality. It's recommended by Duelist for test bench architecture. We work a lot with ESA, European Space Agency, to extend the functionality. I'll come back to that in a moment. It's available in IEEE standardization open, and most people download it from GitHub. And it runs on basically any VHDL 2008 compliant simulator. So whenever I do a presentation, whether it's design or verification, I normally talk about what are the enablers for quality and efficiency. I think that's extremely important. And of course, as you all know, it's structure and architecture that's the most important. And one of the reasons for that is because we want to have good overview and readability. So in my opinion, overview and readability is the most important for design and verification. Of course, also modifiability, extensibility, maintainability, and debuggability. It was mentioned previously here that verification constitutes around half the total project time, and debug takes around half of the verification time. That means debugging, on average, according to Wilson Research, consumes 25% of the total project. That means we have to improve debugging. And that is also what UVM is trying to do. And of course, reusability is important everywhere. And I think it's important to also add the aspect of simplicity here, because you want things to be as simple as possible. But when you have an advanced test bench where you want to test a complex device in the test, then of course, everything cannot be simple. So what we have done in UVM is to make sure the most important things are simple, like the commands that Marcus showed you for controlling the test sequencer. So it's dead simple to read a UVM test sequencer. Of course, your best practices is important here. And when you have done this, it also significantly affects schedule, time to market, mean time between failure, product life cycle costs, and so on and so on. And of course, your next project. And what I've seen is that for simple projects, you can easily save several hundred hours. And for really complex projects, I have seen cases where you could actually save 2,000 to 3,000 hours. So I mentioned the ESA projects. I think that's important to just mention here because we work a lot with ESA on that. They were initiated in order to solve challenges on verification of FPGAs and FPGA IP to provide the best possible VHDL verification methodology, both for the suppliers to ESA and to the VHDL community in general. The first project was started many years ago in 2017, where we added scoreboards, monitors, error injection, transaction info, watchdogs, and so on and so on. Quite a few important issues that were added to UVVM then. Then a few years later, we added what we call enhanced randomization for constrained random, optimized randomization, functional coverage, and also some extensions on that. We also then added HDL regression, as has been talked about here previously. Then last year, March last year, we started on a third ESA project. And from that, so far, we have published what we call completion detection and detection of unwanted activity. And I think it's, in particular, this detection of unwanted activity is extremely important because that's not something that is normally done in test benches. So if the device in the test is actually doing something it shouldn't do, you're very often not testing for that. You're just testing for the things you expect it to do. And we're also adding quite a few more things. And I think in Q2 this year, we will also publish some more additional stuff. So talked about that, what enables quality and efficiency. And as I said, UVM tries to target all of this. So this is the complete UVM system. We have the utility library, which is, I'll talk about in a moment, lots of infrastructure commands. Then we have bus functional models that you need. Then we have transaction leveling models and verification components, also shown by Marcus here. Then we have constrained random functional coverage. We have watchdogs. We have monitors, scoreboards, error injection, and then specification coverage, which I'll talk about in this presentation. So a full-blown verification environment to verify FPGAs and ASICs, by the way. But before I dive into specification coverage, I just briefly want to talk about utility library and BFMs because that's the sort of an entry level into UVM. So assume that you are going to verify, in this case, a very simple interrupt controller. It has a clock and a reset. It has what we call a simple bus interface. It's a dead simple processor interface into the registers. Then a number of interrupt sources and a resulting interrupt to the CPU. So it's a dead simple module, just to show this as an example here. Then we make a test bench around that. And of course, the first thing we need in any such test bench is to have a clock generator. And in UVVM, that's dead simple. In the utility library, you have lots of procedures for generating clock generators. And the nice thing about procedures in VHDL is that if you put them into the architecture rather than into the process, it works as a so-called concurrent procedure. And a concurrent procedure in VHDL is almost exactly the same as a process. So it's an extremely efficient way of reusing processes. So just pick one. Clock generator, this is the simplest version of that. We have far more advanced versions as well, with just the clock signal and a period. And then you have your clock running. Then we have the test sequencer, which is there to actually verify the functionality of your device in the test. So let's show you some of the commands that we use from utility library as a basic entry level of UVM. In my opinion, logging is extremely important because debugging is important. And in order to do proper debugging, you need to have log messages, progress reports. So in this case, we're doing a logging, and we show the result in blue here, what you get out in the transcript. So just get a message saying what you're doing in this case. And then, of course, what you're doing in the test bench is to check values over and over again. In this case, we're checking that the interrupt to the CPU is 0. Otherwise, it will give you an alert. And the default alert is always error. You can change that. And then you notice there's also a message share. And that's a part of the methodology of UVVM. We want to have not only a library, but also a methodology. And a good methodology is to always tell the user what you're doing. Anyone reading your test sequencer, and anyone seeing the output in a transcript. So here you see, first of all, on the command, what you're doing, and then, of course, also in the transcript, what you are doing. You're checking the value, it's OK for a standard logic of 0, and then you have the message saying, actually, what did I do here? And for debugging, this is extremely important. Then very often you also want to check that signals have been stable for a given time, because you can't sample it all the time. In this case, we're checking that the interrupt has been stable from reset time until now. And then you also see the result in the transcript. Of course, this is an interrupt controller, so you want to generate pulses into this interrupt sources. So you just do a gen pulse on the interrupt source number 3, setting that to 1 for 1 clock period. There are other ways of doing that as well, but this is just one way of doing it. And an extremely important part of any test bench methodology is to never wait for something without a timeout. Because if you're waiting for an interrupt, it doesn't come, you're just waiting forever, and you have absolutely no idea why the simulation doesn't progress. So in this case, we do an await value. We wait for the interrupt to the CPU to go to 1, at the earliest after 0 nanoseconds, at the latest after 2 clock periods. If it doesn't happen within this time window, you will get an alert. And also want to mention the BFMs. It's not a part of the utility library, but it's part of the BFMs for various interfaces. In this case, it's a simple bus interface, simpler than AXI-Lite. And in this case, basically, you're doing a write to the interrupt trigger register with a given value. And you can see also the result there. So this is just a simplified transcript. I removed some of the columns just to make it easier to see on the back there. And all those of these procedures come with positive acknowledge. So you can see in the transcript here that all these commands are given a positive acknowledge. This is great when you start using it and when you want to do debugging. Not so great if you're just running regression test. But in that case, you can just filter them out with verbosity control. Also have alert messages and mismatch reports if it fails. And of course, you can count alerts and stop on, for instance, the first error, the third error, 15th warning, or whatever. So there are lots of free BFMs and verification components with UVVM. These are all free, they are all open source, and they're well documented. And there are also example test benches for every single interface. And by the way, if you go in and download the UVM repository, that only includes some demo test benches. So if you want to see the real maintenance test benches that we use for every single verification component and BFM, then you have to open the supplementary, UVM supplementary repository. And the reason for putting it there is because it consumes more space. So this is just showing you a number of the other commands that are available in the utility library, which I said is the sort of entry level. So you can check for stability, clock generators, simple randomization, semaphores, synchronization, and so on and so on. Lots of different functionality. And of course, we do proper documentation. So if you go into the GitHub, for instance, because that's where people normally start, then you'll find this page under UVM. And then down to the right there, you'll see there's a link to github.io. And if you go in there, you'll find the proper documentation. You find that also in the download, but this you can find on the web. So in this case, you can see the complete documentation for UVM, all the different chapters. And then, of course, if you go into the utility library, you can open up that and get more information on utility library. And you also see that it opens up a large section to the left there, seeing what you can find on the utility library. So for instance, if you go into methods, you will find a section on all the methods that you have there. Methods basically means procedures and functions here. And so for instance, then if I want to look at logging and verbosity control, I click in there, I find a lot of commands that are related to logging. And then to the right there, you see the overview of logging and verbosity control. And if I want to look at one specific command like log, I just look at that, and I'll find first an overview, what it's doing, the actual command. Then I'll find the syntax, lots of different variants on that syntax. Then I see all the parameters I can use within that command. And then you can find various examples on how to use it. So it's really very well documented. And yes, this shows you so many variants of the log command where you can extend it and use it in advanced ways. But we always try in UVVM to also make it extremely simple to get started. So that means, in this case, this is the simplest log command you can do, just log with a message. But of course, then you can do everything else here as well to make it more advanced. Now on to specification coverage. What is specification coverage? It's basically something you do to assure that all the requirements in a specification have been verified. It's called different things: requirements tracking, requirements coverage, traceability, and so on, all the same thing. It has some similarities with functional coverage, but it's definitely totally different things. We have functional coverage in UVVM, and that's a totally different set of commands. Specification coverage is then handling this. And that's because most requirements cannot be marked as verified or covered just from one or a few values. What you basically do in your test bench, manually, automatically, whatever, is that when you want to verify something, in this case then, you would write to some registers, you would set some inputs, you would read some registers, you would check some outputs, and then you would think, yes, now I verified this requirement. So, and that's what we do in UVVM. So it says there, most often involves multiple test steps in the test sequence. I'll come back to that in a moment. And of course, also application area and different customers require different reporting views. Come back to that. So when we want to trace these requirements, then of course the first thing we need to do is to specify requirements. Often we get a specification from a third party or whatever. Sometimes we make it ourselves. But anyway, we have to get a list of requirements, of course. In this case, I'm just showing a dead simple example with a motor controller. We only have 4 requirements, just to show you an example. Then we report coverage from our test sequencer or other parts of the test bench. And then we generate a summary report at the end from one or multiple test cases. And here we want to report different things. We want to report coverage per requirement. We want to report test cases covering each requirement and requirements covered by each test case. This is called requirements traceability matrix, and that's required for lots of different things. I'll come back to that. And as I said, we accumulate that over multiple test cases. It's required, it's mandatory actually, for safety and mission critical systems. And it's used a lot for DO-254 and ESA-NASA projects. I would say it's strongly recommended for any projects where you want to have a certain quality. And you have a specification for that. There are expensive tools existing, but UVVM has this for free and open source. There are actually also open source system that gives you some of this functionality. But thing is that reporting that the test case has finished and accumulating that over multiple test cases is not really sufficient. It's not efficient, definitely. Because what if multiple requirements are covered by the same test case? Then, of course, you want to do that in one test case, not in multiple test cases. So in this case, for instance, we're moving or turning something to a given position. So we first have a requirement to acceleration, then to top speed, then to deceleration, and to end up at the wanted position. 4 different requirements, and in most cases, this could be 20 or 50 requirements as well. It's just to simplify this. Then, of course, you could run 4 different test cases for that, 1 for each of the requirements, and then accumulate the result of these test cases. That's possible. But what you want to do, of course, is to do this in one sequence because it's possible to do it in one sequence. And that means you save a lot of simulation time. And of course, this is showing 4 requirements. If you have 20, as I said, you save a lot more. Yeah, and then again, generate the various types of reports. Let's look at an example case here with a UWatch, showing again 4 simple requirements. Yeah, these are requirements. Just to show you an example, they're not really good requirements, but anyway. So in this case, let's start with a single test case, testing all the requirements. And I'm going to show that in a sort of flow diagram-like thing here, graphical here. So let's start by the first thing we need to do, which is to extract the requirements. And what we do then is, well, whatever way you actually handle your requirements, it could be Excel, it could be Word, whatever, you need to extract the requirements and put them into a CSV file. So here we have the syntax to the right and an example in the middle here showing you this CSV file for these 4 requirements. And then we want to implement a test case that tests this. So to the right, you now see the inside of such a test sequencer. And then, of course, we want to run this test case. And when we run this test case, the first thing that happens is that we use the command initialize requirement coverage. When we do that, basically what we do is to make a partial coverage file, also CSV file. Then we start testing things. We make sure that the requirements, in this case, requirements 1 and 3 are covered by reading registers, writing to registers, I/O, and so on. And then we say tick off these requirements. It's been ticked off, put into the file, into this partial coverage file. Then we continue doing that throughout that test sequencer, adding more stuff, and at the end, we finalize the requirements coverage, and that gives us also a stamp at the end of this file, because if something has gone wrong, if we have hit upon an alert, an error or something, then it will not give you a pass at the end, it will give you a fail at the end. So it's important to actually reach the end here to get the stamp at the end. And as I said, this is known as partial coverage because it's for one test case only, right? Then you want to compile all of these test case results from different partial coverage files. We do that with a Python script. So when you run that Python script, we generate these requirements traceability matrix. So the first thing we generate is requirements versus minimum of covering test cases. But since we only have one test case in this case, we also cover the second one, requirements versus all covering test cases, because there is only one in this case. And then a test case versus requirements result file as well. So what if we have multiple test cases? Let's again look at simple usage. Then normally any test can be run in any test case, depending on the requirements you have from the final customer. So for every single test case, you have to have inside your test case this sequence I just showed you. You have to first initialize requirement coverage, you have to tick off the requirements, and then finalize requirement coverage. When you have done that, you generate your partial coverage file. They also use the same requirement list, and you get a unique coverage file per test case. Could also have multiple test cases inside the same test sequencer. So the only thing you have to think about then is you always have to do the same thing over and over again. Initialize, tick off, and finalize. And then you can do that multiple times inside that same test case if you like. And after running all the test cases, as I said, then you run the Python script as before, but then you include all the different coverage files. So let's assume you have multiple test cases. Then Each test case in VHDL will generate this partial coverage file, as you see here. So we have a partial coverage test case called TC Basic, which tests the UART requirements 1 and 3. In this case, they both pass. And then we have a similar test case and a similar partial coverage file for the other test case and for the third test case. In this case, 3 test cases that covers everything. Again, for simplicity. Of course, this could be 50 or 100 test cases as well. No problem. So this is just to illustrate the usage. Then we use the Python script again to accumulate all the coverage. And as I said, we want to generate this requirements traceability matrix. And now we have multiple test cases. So in the first instance here, we have requirements versus minimum covering test cases. See that to the bottom left. And then you see you have the requirements versus all covering test cases, and then your test cases versus requirements. So what if a test fails? Then this is the result I just showed, where you have everything working, everything passing, and you see the partial coverage file. Then if one fails, you will get a result saying in this partial coverage file that it did actually fail, caused by the error in test case, of course. And then the summary files, that gives you the total summary of all the test cases. We had a look at that in the previous slides, to the left there. And to the right, you'll see what happens if something went wrong. So in this case, you can see that UART requirement 4 fails because the requirement failed in the partial in the test case. And then you can also see that it also fails or makes it non-compliant on requirement 2 and 3. And that is because that test case failed. Because if something fails in a test case, we cannot really be sure that what happened previously in that test case were okay. So we fail them as well. What if we have advanced specification coverage? Then we could specify the required test case for any given requirements. We could specify that at least one of multiple test cases must pass, but not necessarily all. But if they are executed, they have to pass, of course. We could specify the requirement is tested in multiple test cases, if that is a requirement. You can map requirements in one file to requirements in another file. And that could be extremely useful for 2 different things. One is to allow reusable test benches with the coverage included. So I've done a simulation 2 years ago with everything I talked about. And then I want to include that in a new project, but then suddenly the list of requirements is slightly different. Then I can map the new requirements to the old requirements. Or if I have compound requirements, I can split them into more detailed requirements as well. Yeah, and again, of course, as in the previous case, we have proper documentation. You can find that on this GitHub IO as well for specification coverage. Let's look at how you can get started with specification coverage as a step-by-step demo. First thing we need to do, of course, is to include the UVVM utility library and specification coverage. That's just this simple code here, including the library and including the packages. Then we're ready to go to basically use any of the commands that are available with specification coverage. So take the simple case first, where we have no test case specified. Then we have this requirement list, in this case 5 requirements. And then in this case we have 2 parameters only, so the test case is not specified here. But please note that for DO254, for instance, you need to actually specify the test case as well. This is a simple example. Single test case only, again, to make it simple, all requirements being covered. First thing, again, you should always do, and in my opinion, is to make a log. And then you can see the result here in the transcript, see the result of the log, and then you see the result of initial requirements coverage. First, it reads the requirements file, and then you can see it also reads all the requirements, and you can see also the comments that are in these files. And at the end, it closes the requirements file. Then we continue, and we tick off these requirements. And then you can see in the log here what happens in the log. It logs that the requirements are passed. And then you can keep on doing that for the next 3 requirements as well. And you also see that in the transcript. And then you continue with the last requirement. I thought it was until 10 minutes to 40 minutes. Sorry? Okay, yeah. Yeah, thanks. So this is the last requirement we're going through. And then we see the result of that. And then we do the finalized requirement coverage. And you can see the result of that also in the transcript. So you can follow everything that happens. And of course, here as well, you can also remove all of these transcript messages if you don't want them. And again, we make this partial coverage file, a simplified version. And then you want to make the coverage summary. So again, we use this Python script to make a summary. And this is what you get in the actual, when you actually run it. You can look at the results, you can look at the requirements, and a passing test case. And then we get this summary file saying that everything is compliant in this case. Now, if we have specified a test case, because very often we have to do that, especially for ESA, NASA, DA255, and safety, and so on. So in this case, we specify now where should these requirements actually be tested? Which test case should test them? And same as before, obviously, but in this case, of course, we need to run all these 3 test cases and then generate a partial coverage for all of them. So we get 3 partial coverage files, as I showed you in the previous slide, with these different results. We prepare the post-processing, and when we have multiple partial coverage files, we could list all those files in a text file, so we don't have to list them all the time in a Python script. So we just make a text file including all the partial coverage files that we're using in our project. And then, rather than including all the arguments on the command line, we make a configuration file. It's just a config.txt where we have all the different requirements and switches and so on. And then we can just run the Python script on that configuration file to generate the summary files. And then you get all these compliance files. So summary on specification coverage. Specification coverage doesn't say anything about absolute quality, because you have to make sure that you are testing the things that you want to check. So it depends on the developer actually testing the right stuff. Depends on a good requirement specification. All the relevant requirements should be included. You might actually have to split them up sometimes in lower level requirements. But given a good test case that do what they intend to do, then specification coverage will actually track and assure that all requirements in the specification have been verified. And what I see from time to time, or quite often actually, it's quite common in many projects to just sometime during development tick off somewhere that a particular requirement is tested. And often that is only done as a mental exercise in some person's head, which is not good at all. It's always, in my opinion, always better to use a written, repeatable, and automated approach. And this verification IP and specification coverage applies that and allows you to do that in a very structured way. Time to summarize. UVM is used by lots of FPGA and ASIC designers for ESA, NASA, mission critical designs, DO254, high quality in general. And UVM specification coverage was something that we developed in tight cooperation with ESA because they needed this as well. And we now updated it quite a bit also in the latest ESA projects. So I think the last updates there actually were only a few weeks ago. There's no lock-in on UVM. So you can basically pick any part you like of UVM. If you like a verification component for Axie, for Avalon, whatever, you can just pick that and use it in your legacy test bench. Or you can use the complete environment, of course. That's up to you. So there's no lock-in. and it works with any other VHDL test bench methodology, and will result in significantly improved quality and also improved efficiency. And I would say also in this case, far less boring and time-consuming manual documentation that you normally have to do if you want to make this requirement traceability matrix. That's it. Thank you.
Thank you, Espen. Very clear and inspiring. I will definitely test it.
Good.
Any question? Yeah.
Hello, Espen. Thank you very much. Since it's quite complicated system, I mean, extended as capabilities.
Sorry, I can't hear you properly.
Yeah, since it has quite a lot of capabilities options, the UVVM system. So to get started with an existing complex design, right? Would you suggest going through some VVCs that you already showed that there are available in the library, and then maybe some scoreboard? What would be an approach for an existing design?
To get started?
Yeah, applying this.
Yeah, the way to get started, I mean, there's lots of different ways to get started. I mean, basically you could, if you have a legacy test bench and you want to check for specification coverage, you can just use this verification IP independently. If you want to start using UVVM in general, then I would start, as I mentioned on the first slides, with the utility library and the BFMs. The BFMs in UVVM are simple procedures. And that's again because we want it to be easy to get going with UVVM. And then
picking up the appropriate that matches your own design, right?
Say again?
Picking up the appropriate BFMs that match your specific design needs.
I didn't get that, sorry.
Yeah, we're talking about having already a complex design, which then you want to introduce into VVM.
You already have a design, already have a test bench? Or?
You have the design, just the design.
Design, yeah.
That's what you have.
Yeah, and if you then wanted to use UVM, if you have no contention issues, let's assume that you have this simple interrupt controller. If you have a simple interrupt controller, simple CRC, simple filter or something, then you can use the BFMs and BFMs only because that's all you need. If you have a design where you could have a contention, that is, there could be problems when you, for instance, apply data on one interface at the same time as you apply data on another interface, maybe reading data out on a third interface, then you should go for the verification components because they allow you to, from the test sequencer, just send out commands to every single verification component so that they can all start at the same time. That means you can control everything from one single test sequencer, but the commands are distributed to verification components so they work in parallel. And that way you can actually skew, for instance, one interface access over another and detect corner case problems. So if you have that kind of scenario, then you should use verification components. Yeah.
So, yeah, Marcus.
So there are project management tools that include requirements management. Usually, in bigger projects, they have some kind of tools in the project management that where project managers tick requirements or define requirements. So is the CSV format you use a standardized format? So could you export the requirements from these super expensive tools to use it directly, or do you have to convert it somehow? So is there a standardized format for requirements?
No, this is not a standardized format. It's not. What is sort of standardized is the requirements traceability matrix, where you have to give test cases versus requirements. That's what is required from this requirements traceability matrix. But we know that it could be multiple different sources for the specification. It could be doors, could be advanced tools, could be Word, Excel, whatever. I mean, yes, people use Word and Excel. And if you have that, it's not that difficult to actually export this to a CSV file. If the requirements are labeled properly, it's quite simple.
Yeah, and this CSV file is really simple. You have only 2 columns and
Yeah.
just the label and the text.
Yeah, and the third column, if you want to also include a test case,
Test case.
which I said is required for high-quality systems. Yeah.
So, sorry.
So my question is also regarding the requirements tracking. So do you have any tools to extend it, if you do hardware software co-design, for example, to cover also the requirements for software where you have unit tests?
Yeah, no, this is only for the FPGA. Yeah,
Okay.
sorry.
Maybe very naive question from my side. Just imagine I'm a OSVVM user. If I want to use only this feature for UVVM, I just need to call this library and it's compatible, let's say.
Yeah, yeah, no problem. Yeah.
So, yeah.
That simple.
Yeah, so definitely worth trying.
Yeah.
No other question online? No? Okay, so otherwise let's thank
Yeah.
Espen again.